In the previous video, we recalled the definition of the linear momentum of a particle of mass m with velocity v. G is equal to mv. We also wrote the balance of linear momentum F is equal to g dot, or the linear impulse linear momentum equation, which is the time integral of the balance of linear momentum, the integral of f dt. Here f would be expressed as a function of time, is equal to g at t2 minus g at t1. The integral of f dt between t1 and t2. And we said that the linear momentum of a system is conserved. G is conserved if g dot is equal to 0, meaning that f is equal to 0. Now there are conditions or systems in which the linear momentum is not totally conserved. F is not equal to 0, but the linear momentum could be conserved in a certain direction. So let U be a unit vector. Expressing a certain direction, or representing a certain direction, or expressing a certain direction. U need not be fixed. For example, we can consider Ex, Ey, but also the polar basis, Er, Etheta, Et, the Serif-Frenet basis components, etc., etc. So let U be some unit vector, and under what conditions is the linear momentum of a system conserved along U? Under what conditions is G dot U equal to a constant, meaning that the linear momentum along U is conserved. Linear momentum of the system along U is conserved. Okay. Well, let's take the derivative of this expression. If G dot U is equal to a constant, then the derivative of that expression is just equal to 0. And on this side, on the left-hand side, using the product rule, I'll get G dot U plus G dot U dot. Remember, U is not constant. That's equal to 0. And I can replace G dot by F. F dot U is equal to, or plus G dot U dot is equal to 0. That's our condition for conservation of linear momentum along U. For conservation of linear momentum along U. Now if U is fixed, then this condition simplifies. F dot U is equal to 0 and U dot is just equal to 0. Okay, if U is fixed, then F dot U is equal to 0 is enough to say that the linear momentum of the system along U is conserved. Let's consider an example, projectile motion. So let's say I have a projectile, gravity is pointing downwards. So if I want to draw the free body diagram of the projectile, the only force acting on it is its weight. Now, notice that the sum of forces along the horizontal is equal to 0 because the weight is purely vertical. Well, this just means, looking at this condition, that the linear momentum of the projectile along Ex is conserved. Ex is fixed, so I do not have to worry about this larger expression. Now, is the linear momentum of the projectile conserved along Ey? think about it. The answer is no. Right? Because f dot ey is not 0. That's the projection of the weight along ey, which is non-zero. Okay, so that was easy because ex and ey are fixed. We're gonna go through examples later where ex and ey are not fixed. In those examples, you have to be careful to apply this more complicated expression. F dot u plus g dot u dot is equal to 0. That's what you need to show to argue that the linear momentum along u that is moving is conserved. Great, thanks.